I guess without further ado, we can get started. What does gravity look like? To many of you, it might look like the arced flight of a baseball or leaves falling from trees. We see gravity by the way it impacts the objects we interact with. But the scope of our experience with the universe is narrow, and so too is our perception of gravity. There are black holes on the other side of the universe that we cannot see, yet we know that they're there. How? Gravitational waves are ripples in the fabric of space and time radiating from the movement of the most massive objects in the universe. To measure them, we need a gravitational wave detector the size of the Milky Way galaxy and made of exotic stars. Tonight, I want to tell you how my colleagues and I are building a gravitational wave telescope out of stars. But before we can build the gravitational wave telescope, we first need to understand what gravitational waves are. And that starts with Einstein's theory of general relativity. Einstein's theory describes the fabric of the universe by 4 dimensions: 3 dimensions of space and 1 dimension of time. A dimension is just a direction an object can move, like up, down, left, right, forward, back, and forward in time. Now, I'm going to start our description of general relativity out with the standard science fair bowling ball on a bend sheet demonstration. But since the stores were fresh out of 4D fabric, we're going to start with a simplified 2D version of a universe. Okay, welcome to our 2D universe. Objects in this 2D universe can move anywhere along the surface of this fabric. They can move forward, backward, they can move left to right, or they can move some combination of the two. But every being that lives in this universe is stuck on the surface of this fabric. And fundamentally, objects with mass, like a planet, for example, warp this fabric. Now, here we're only seeing the warping of 2 spatial dimensions by this planet. But if we wanted to see how a massive object warps all 4 dimensions, we could do that like this. Now, of course, we can't perceive 4 dimensions, so we have to come up with some sort of clever representations. And this is just a clever representation of 4D space-time. So we have our massive object at the center, our planet at the center, and then we have this cube. But you'll notice that the grid lines of the cube, they're not straight, they're curved. They're curved by the presence of this massive object. Not only that, they are more curved closer to the massive object than they are further away. So this massive object is warping the 3 dimensions of space, but it's also warping the dimension of time. Notice that the clocks that are closer to this planet are ticking more slowly than the clocks that are further away. So this is how a massive object warps 4 dimensions. But just for the simplicity of explanation, let's go back to our 2D universe. Okay, so if I introduce another massive object into this universe, like a moon, for example, its path is bent toward the planet. General relativity shows us that this deflection of objects by the curvature of spacetime is the true definition of gravity, not an attractive force, as our experience and introductory physics classes would lead us to believe. To summarize general relativity in 2 sentences, matter tells spacetime how to curve, and the curvature of spacetime tells matter how to move. Matter tells spacetime how to curve, and the curvature of spacetime tells matter how to move. Now, a planet may deform spacetime like this. A star would deform it even more so, because the amount of curvature depends on the mass of the object. And a black hole will pinch space-time to an infinitesimal point so drastically that not even light can escape. Now, before we start making some gravitational waves in our 2D universe, we need to address one more property of space-time. Both our universe and this 2D universe have a speed limit. That speed limit is the maximum speed at which information can travel. The speed limit the speed of information in our universe is about 980 million feet per second. Nothing can travel faster than that. Most things travel slower than that, and some things travel at that speed. Light, for example, travels at that speed limit, which is why the speed of information is often referred to as the speed of light. And the speed of light and information, it's the same everywhere in the universe. What that means in practice is that two distant parts of the universe cannot instantaneously communicate with each other. And the further away 2 points in space are, the longer it takes for information to travel from one point to another. What that means, so if, for example, the sun, which is 8 light minutes away from us, were to spontaneously disappear, it would take 8 minutes before the sky became dark. Similarly, it would take 8 minutes before the gravitational effect of the sun's absence reached us, and Earth is flung out of its orbit because deformations in space-time, gravitational waves, also travel at the speed of information. I can demonstrate that by the help of our little astronaut friend here, by suddenly introducing a massive object into this universe. The way that I'm going to do that is just by flicking down on the fabric. There we go. We've introduced that massive object. But that was pretty quick. So let's take a look at that in slow motion. So you can see that our astronaut is not yet aware of the new massive object that's been introduced, because the warping of space-time is traveling outwards from the source at the speed of information of this sheet. And that information hasn't reached her region of space yet. Only now does she feel the presence of that massive object. Now, in reality, massive objects don't spontaneously appear or disappear, but they do move. And in particular, they move in orbits. We can illustrate an orbit just by pressing my fingers down into the fabric, showing how, two massive objects would deform space-time, and I can move my fingers around each other, but I can't really go a full rotation, and I can't do it very quickly. So I've made this little model to illustrate how two orbiting objects would deform space-time. I just press them into the fabric and show how space-time warps as they orbit each other. Now, this configuration of objects is known as a binary system. Now, you'll notice when I spin this binary system, let's just call them black holes, for example. As I spin this binary system around, you'll notice they're not producing any gravitational waves in our 2D universe. And that's because in order to produce detectable gravitational waves, these objects either need to be much more massive or they need to be orbiting much faster. Now, I can't make the wheels any bigger, but I can make them orbit faster. To do that, I'll need to bring in some heavy artillery. So I'm going to use this power drill to spin our binary black holes at the speed of information, fortunately not the speed of information of our universe, but the speed of information of this fabric. And hopefully we should see some gravitational waves. So to produce gravitational waves, you either need very massive objects or very fast spinning objects, like we have here. Now, let's take a moment to discuss some properties of gravitational waves and waves in general. Now, we haven't labeled our coordinate system yet, so let's go ahead and say, for the sake of explanation, that each of these squares is 1 light year on a side. That is the distance that light and gravitational waves can travel in 1 year. Now, one fundamental property of waves is the wavelength. Very simply, wavelength is the distance between consecutive peaks of the wave. So if each square is 1 light year, and the peaks of these waves are 3 squares apart, we would say these gravitational waves have a wavelength of 3 light years. Another fundamental property of waves, which is directly related to the wavelength, is the frequency. The frequency of a wave is the number of wavelengths that pass a region of space per unit time. Since we know the wavelength is 3 light years, and we know that gravitational waves are traveling at the speed of light, we can easily figure out the frequency. So let's count how long it takes one wavelength to pass by this region of space. So we'll start with 0 years as the first peak passes this point, and count until the next peak passes. Ready? Go. Okay. It takes 1 year to travel 1 light year, 2 years to travel 2 light years, and 3 years to travel 3 light years. Let's do that one more time. First peak is passing. 1 year to travel 1 light year, 2 years to travel 2 light years, and 3 years to travel 3 light years. Since one wave passes this point every 3 years, we would say the frequency of these gravitational waves is 1 per 3 years. Now, the frequency of gravitational waves is proportional to how fast these compact objects are orbiting each other. So if the orbital rate increases, the frequency of the gravitational waves they produce increases. Still, we've not quite gotten to the full picture of how gravitational waves distort space-time. And that's because we're still working within this simplified 2D universe. Recall that general relativity says our universe has 4 dimensions. So let's step up by 1 dimension and see how gravitational waves distort 3 dimensions of space. So notice that the top of this gravitational wave is moving in a similar way that our 2D fabric was moving when we spun our binary black holes. But that's not all that's happening. So while the top of the wave is moving up and down, and the up-down dimension is expanding, the left-right dimension is contracting. And then when the up-down direction contracts, the left-right dimension is expanding. So these rings, which are meant to represent different points along the path of a gravitational wave in the 3 dimensions of space, as the gravitational wave passes, they get tall and skinny, and then they get short and fat. So what would actually happen to objects embedded in space-time as a gravitational wave passes? Oh, so we can look at this over our 2D demo and just see that a little bit closer, that as the peak of the wave passes, right, they get tall and skinny. As the trough of the wave passes, they get short and fat. So how does this affect objects embedded in space-time? The way that I'm going to illustrate that to you is with a dance. Now, I know it sounds silly, but if you want to, or if you're able to, you can actually stand up and join me in this dance. Maybe it'll help you remember it better. And we're going to use this dance to explain some more complicated concepts later on. All right, I see a bunch of people standing up. Awesome. Okay. So I want you to imagine that a gravitational wave is passing from behind me, through my body, and out of the screen. So the gravitational wave is moving in the forward-back direction. My body is oriented in the up-down and left-right direction, right? I'm just floating out here in space. So this is what's going to happen to my body as a gravitational wave passes. When the peak of the wave passes, I'm going to get tall and skinny. And then as the trough of the wave passes, I'm going to get short and fat. Skinny, short and fat. Tall and skinny, short and fat. Peak of the wave, tall and skinny. Trough of the wave, short and fat. This is the way passing gravitational wave distorts space-time and the objects embedded within it. Awesome, everybody's doing it. Great job. Very good, very good. So, if we wanted to see the full picture of how gravitational waves distort space-time, we can combine this dance along with our 2D demo. And that would look like this. So, each Tyler is representing what's happening to space-time at a different point along the path of the wave. Now, I know the wave is going out, it's propagating out in all these directions. I just want you to focus on this direction, the direction along the way Tylers are facing, right? So, peak of the wave passes a Tyler, he gets tall and skinny. Trough of the wave, he gets short and fat. But while one Tyler is getting tall and skinny, another is getting short and fat. So gravitational waves are not distorting space-time in the same direction at all points along the wave. But the thing I really want you to notice is that these Tylers, they're not moving forward and backward as the gravitational wave passes. They're not riding the wave, right? They're staying fixed in one point, nor are they getting fatter or skinnier in this direction, in the direction of propagation of the gravitational wave. Nor would any of these Tylers measure their watches to be running at a different rate. That is because gravitational waves distort space in the directions perpendicular to the way the wave is traveling. So the wave is traveling in the forward-back direction, and the Tylers are shrinking and expanding in the up, down, and left-right directions. They're not moving forward-backward. They're not getting fatter or skinnier this way. And their clocks are not running at different speeds. They're just changing in the directions perpendicular to the way the wave is traveling. And we can put that blue wormy thing over top of that to see what that looks like along continuous points along the path of the wave. So while I'm only showing the distortion in one direction, in reality, it propagates out in all directions, away from the binary system, stretching and shrinking everything as it passes, stars, planets, solar systems, galaxies, and us. The goal of gravitational wave astronomy is to measure this motion. Remember, the amount of stretching of space-time is related to the mass of the objects in the binary system. And the frequency of gravitational waves is related to the orbital frequency of the binary system. So by measuring the magnitude and frequency of these distortions, we can understand the binary systems that generated these gravitational waves. So how do we measure it? The issue is that all these binary black holes are far away from us, though perhaps that's for the best. And the strength of the waves falls off quickly as you move away from the binary. For the binaries we've observed, at distances of hundreds of millions of light years, the distance between Earth and our nearest star, Alpha Centauri, due to a passing gravitational wave, that distance is only changing by the width of a human hair. How could we possibly hope to measure distortions in space-time that small? If only we had something that traveled really quickly and always at the same speed. We could send it between 2 points in space, and if it arrived early, we would know that the distance had shrunk. And if it arrived late, we'd know that the distance expanded. What do we know that travels really fast at the same speed no matter where you are in the universe? Light. And that's exactly what the Laser Interferometer Gravitational Wave Observatory does. LIGO has 2 identical observatories, one in Washington and one in Louisiana. Both consist of 2.5 mile long tunnels at right angles. Inside these tunnels are 4 mirrors and 2 laser beams in a vacuum to keep them isolated from external vibrations and temperature fluctuations. What LIGO does is measure the time of flight of these laser beams so that when a gravitational wave passes through the detector, one dimension shrinks and this beam arrives early. Then the other dimension shrinks and this beam arrives early. Then this one, then this one, this one, then this one. Back and forth, one beam arriving earlier than the other in the characteristic motion of gravitational waves. Now, LIGO was the first experiment to make a direct detection of gravitational waves in 2015, winning them the Nobel Prize. The gravitational waves that LIGO detects come from merging solar mass black holes, the kind that form when two massive stars collapse under their own weight. Now, LIGO has made dozens of detections since 2015, ushering in the era of observational gravitational wave astronomy. LIGO opened a new way to view the cosmos. From the first humans looking to the sky to try to understand the universe until 2015, nearly all of the information we had to study the universe came from light waves. But now we have a new messenger, a new way to study the dark parts of the universe, gravitational waves. But LIGO has its limitations. You see, LIGO is really good at detecting gravitational waves from solar mass black holes that are spinning quickly, but they're relatively tiny. But there are lumbering behemoths out there that escape LIGO's sight. Observational evidence suggests that nearly every large galaxy contains a black hole at its center, 1 million or 1 billion times the size of the solar mass black holes that LIGO can see. These black holes do not form from stellar collapse like the LIGO black holes, but by merging with other galaxies. And galaxies are merging all the time, all across the universe. That's the only way you get galaxies as massive as the Milky Way and Andromeda, by smaller galaxies merging to form bigger galaxies, which merge to form still bigger galaxies. And when these galaxies merge, so do the black holes at their centers, forming supermassive black hole binary systems. Remember, I said there's two ways to produce gravitational waves. You can spin some smaller black holes very fast, or you can spin some giant ones slowly. These are the latter. But here's the key thing that make gravitational waves from these supermassive black hole binaries different than those detectable by LIGO. Because they take so long to merge, there's not just one merging at a time. There's not even a handful of merging at a time. No, the combined gravitational waves of all of the supermassive black holes merging over cosmic history, different sizes and frequencies, add together to form a low-frequency hum of gravitational waves. A gravitational wave background. Allow me to explain with an analogy. Imagine you're eating lunch in a crowded cafeteria. You can hear the conversations of your friends at your table because they're close by and therefore louder. But you can't hear the conversations of everyone else in the cafeteria. They just form a loud background hum. Your friends are the individual sources of gravitational waves, the individual supermassive black hole binaries. Everyone else in the cafeteria is the gravitational wave background, the sum of all of the other gravitational waves from all of the mergers across the universe. Now, we actually have estimates for the number of supermassive black hole binaries based on observations using light waves. Now, those estimates for the amplitude of how loud that background is come from just looking around with optical telescopes and counting how many galaxies there are. That's like counting how many people are in the cafeteria versus listening for how many people are in the cafeteria. Based on these estimates from optical telescopes, we think that the amplitude of the gravitational wave background is louder than the individual sources of these black hole binaries. That means that everyone else in the cafeteria is so loud you can't hear your friends' conversations. By studying the statistical properties of this background hum, we can begin to understand the history of supermassive black hole mergers across cosmic time, and by proxy, galaxy evolution history. Maybe we'll find that maybe we'll find that the background is louder at lower frequencies, indicating that these binary mergers take much longer than we expected to occur. Or maybe we'll measure an uptick at some frequencies, indicating some loud voices among the crowd. But in order to detect and measure this background, we have to be clever. Like I said, LIGO is really good at measuring the small solar mass black holes that are spinning very quickly and produce gravitational waves that have wavelengths, from on the scale of a few miles to the size of the Earth. But these supermassive black holes, they take years or decades to merge, producing gravitational waves that have wavelengths of light years. A miles-long gravitational wave detector like LIGO can't possibly hope to detect gravitational waves that are light years long. If only we had lasers being beamed to us from light years away. Fortunately, nature has provided these for us. When a supergiant star, about 20 times the mass of the Sun, runs out of nuclear fuel, it can no longer support its weight against the pull of gravity, and it collapses under its own weight. The pressure at the center of this collapsing star is so great that the electrons get forced into the nucleus of their atoms. Now, if the core of this star can stave off total collapse, the outer layers will rebound off the core, flung into interstellar space in a supernova explosion. Now, what's left of the core is a ball of neutrons the size of a small city, a neutron star. In this collapse, the star must conserve its angular momentum. Like a figure skater, pulling her arms in to spin faster and faster, neutron stars are spun up to incredible speeds, rotating dozens of times per second. Now, the magnetic fields of neutron stars are tremendous. Place a neutron star at the distance of the moon, and its magnetic field would be strong enough to wipe the credit card in your pocket. These magnetic fields accelerate charged particles toward the poles of the star at nearly the speed of light. The acceleration of these particles, it is thought, generates beams of radiation from the star's magnetic poles. Now, if these beams are not aligned with the rotation axis of the star, they swing around like stellar lighthouses. We have a special name for neutron stars whose rotating beams intersect with the Earth. We call them pulsars. Now, pulsars emit only very dimly in the visible light that can be captured by human eyes or optical telescopes. Instead, these beams of radiation are comprised of radiolight, which is invisible to humans. Radiolight is the lowest frequency, and therefore lowest energy, light produced in the universe, which is why you need enormous radio telescopes, like the VLA, to observe it. Now, let me just stop for a moment and just clarify something. Light waves, like gravitational waves, are waves. They have a frequency and they have a wavelength. But light waves and gravitational waves are not the same thing, right? Gravitational waves are ripples in the fabric of space and time produced by the movement of those, massive objects orbiting around each other. And light waves are produced by atoms and molecules wiggling and giving off energy. So they're not the same thing. And I'm going to try to be, very clear when in making a distinction between when I'm talking about the frequencies of light waves and when I'm talking about the frequencies of gravitational waves. So if we can't see radio light from pulsars with our eyes or with optical telescopes, what does a pulsar look like to a radio telescope? This is what it would look like. More specifically, the bottom panel is what we would see. Every time the pulsar beam points toward Earth, we see a pulse, hence the name. The shape of this pulse and the spin period, which is the time between each pulse, are our primary sources of information about these objects. This pulse on the bottom panel is a cross-section of the pulsar's beam. And so the shape of the pulse gives us information about the shape of the beam. Now, every pulsar has a different shaped beam. So these pulses are like a unique fingerprint of each pulsar. Now, normal pulsars have periods typically on the order of hundredths of seconds. And searching for these periodic signals in radio surveys of the sky is how we find new pulsars. And by measuring the arrival time of these pulses, we can monitor changes in the distance between the Earth and the pulsar, kind of like the laser arms of LIGO, but on a galactic scale. So, on short timescales, if nothing along the pulsar to Earth line of sight changes, the time between the pulses doesn't change. They arrive regularly, right? Nothing here is changing between the Earth and the pulsar. The pulsar is spinning around. Every time the beam passes in front of the Earth, it sends a pulse, but those pulses arrive at the same interval. However, if the distance between the pulsar and the Earth decreases, the pulse will arrive earlier. And if the distance decreases, the pulse will arrive earlier. And if the distance increases, the pulse will arrive later. Now, the change in distance pictured here and the change in pulse arrival time is highly exaggerated. In reality, the changes in the pulse arrival times, they're only changing by about a microsecond. That corresponds to a change in distance between the Earth and the pulsar of about a foot. You heard me right. We need to know the distance between the Earth and these pulsars to the precision about a foot if we ever hope to be able to detect the gravitational wave background. Remember that gravitational waves are weak, and low-frequency gravitational waves expand and shrink space very slowly. Even though they're spinning very quickly, normal pulsars will eventually slow down on the same timescales as gravitational waves. That means these stellar clocks are drifting over time, so they're not sensitive enough to detect gravitational waves. But there is an exotic class of pulsar which doesn't suffer from this drift. They are called millisecond pulsars. Now, while in general binary star systems are very common, binary systems with pulsars are not. And that's because when one star in the pair goes supernova, the other star is usually obliterated or kicked out of the system. But if the other star survives, you end up with a pulsar with a companion. Now, that's often not great news for the companion, though, because if the stars are close enough, the pulsar can begin sucking material off the companion star, increasing its angular momentum. It's like pulling a ripcord on the pulsar. Now, if the pulsar can continue to mooch off of its companion for millions of years, it can be spun up to thousands of rotations per second, becoming the fastest spinning objects in the universe. With their new lease on life, these recycled pulsars don't suffer from the same drift that regular pulsars do. It would take longer than the universe has existed for one of these millisecond pulsars to slow by even one rotation. They blink at us with atomic clock level precision. So, these pulsars don't drift. Their clocks don't drift because they don't slow down even over tens of billions of years. Now, to give you a sense of how fast these guys spin, I'm going to show you animations I'm going to play some audio for you of a normal pulsar and a millisecond pulsar. So this isn't really what we receive with radio telescopes, right? Radio telescopes receive light, but this is what it would sound like if we were to convert the signals that we get from our radio telescopes into sound waves. So the first is the Vela pulsar. It's a relatively young pulsar, and it's in a supernova remnant, and it spins about 11 times per second. This is what it would sound like if we converted its radio waves into sound waves. Now, that's pretty fast, but it's not fast enough. And this is not one of those pulsars which doesn't suffer from that drift. The Vela pulsar is actually slowing down. But next is pulsar B1937 plus 21, a millisecond pulsar, which spins more than 600 times per second, faster than a high-end kitchen blender. This is what that would sound like if we converted its radio light into sound waves. So these are the pulsars that we can use to detect gravitational waves because they don't drift. So now we have a super accurate timekeeper to keep track of the changing distance between the Earth and the pulsar. So we're ready to detect gravitational waves, right? Well, if the gravitational waves were the only thing changing the distance between the Earth and the pulsar, this would be an easy proposition. But many things besides gravitational waves change the distance between the Earth and the pulsar. So to tease out that specific characteristic motion of gravitational waves, right, from our dance at the beginning, we need more pulsars, and we need more millisecond pulsars. To illustrate why, let's go back to our dance. So I want to imagine again, that there's a gravitational wave passing from behind me, through my body, and out of the screen, right? So the gravitational wave is moving in the forward-back direction, and I am oriented in the up-down and left-right directions. I'm just floating out here in space. But this time, I want you to imagine there's a ring of pulsars around me, and the Earth is at my center. So this is our galaxy of pulsars. So what's going to happen to the pulsars in our galaxy when the gravitational wave passes? Remember, the gravitational wave is passing in this direction. What happens when the peak of the wave passes? What happens when the trough of the wave passes? Well, as the gravitational wave passes, right? Short and fat, tall and skinny. Short and fat, tall and skinny, right? So as the gravitational wave passes, the distance between the Earth and the pulsars is changing in this very specific way, right? So as the peak of the wave passes, right, I get tall and skinny. Some of the pulsars move further away and some move closer. As the trough of the wave passes, I get short and fat, and then the pulsars on the side move closer. How does that affect their pulse times of arrival? Well, when the trough of the wave passes, the pulsars above and below, they get closer to the Earth, and their pulses arrive earlier. So their pulse times of arrival shift to the left. They shift to arriving earlier. And then the pulsars on the left and right, they move further away from the Earth, and their pulses arrive later. And then when the peak of the gravitational wave passes, now the pulsars on the left and right, they arrive earlier. And the pulses above and below the Earth, they arrive later. This is the way that gravitational waves are encoded into the pulsar signals. In this very specific motion, right? In this very specific motion that affects the pulse times of arrival that we then measure here on Earth. This is our gravitational wave telescope made out of pulsars, also known as a pulsar timing array. Now, cartoons are nice, but what would it actually look like to detect the gravitational wave background in our pulse times of arrival data? This is what it would look like. A graph. Don't get scared. We can use our dance to understand this graph. But first, let's talk about, let's break this down a little bit. So what this graph is showing is what it would look like to detect a gravitational wave in your pulse times of arrival data. On the y-axis, we have the TOA deviation correlation. Let's break that down. What that means is for a given pair of pulsars, how would we expect their pulse times of arrival to change due to a passing gravitational wave? So compare any pair of pulsars that you're observing and see how their pulse times of arrival are changing, and that gives you a value on the y-axis. And on the x-axis is the angular separation between a pair of pulsars on the sky from 0 degrees to 180 degrees, which are pulsars that are on opposite sides of the sky. You're probably thinking, I don't see how this graph shows a gravitational wave background in our pulse times of arrival data. Well, that's the power of our dance. So let's come over here to 0 degrees. Remember the dance, right? Two pulsars which are next to each other on the sky, right? When a gravitational wave passes in the forward-back direction, how would they move? They would move like this. They would move in the same way due to a passing gravitational wave. And their pulse times of arrival would change in the same way due to a passing gravitational wave. So we would say they are highly correlated, and this graph is at a maximum. Okay, what about 90 degrees separation, right? How would two pulsars 90 degrees separated in the sky, how would those move due to a passing gravitational wave? Well, that's this part of our pulsar dance. These pulsars are moving in completely opposite directions in the opposite way. And so we would say the arrival times of their pulses are anti-correlated, and this graph reaches a minimum. Okay, what about 180 degrees? Pulsars on opposite ends of the sky. How would they behave due to a passing gravitational wave? Well, that's this part of the dance. They're moving closer to and further away from the Earth at the same time, but in different directions. So we would say that they are partially correlated. This graph is a graphical representation of our dance, of the movement of these pulsars due to a passing gravitational wave. If you were to detect this signal, if you were to observe this trend in the arrival times of the pulses from your pulsars, that would be the smoking gun that you have detected a gravitational wave background. Now you might be wondering, well, have you done it yet? The answer is maybe. This is 13 years of data from the nanograv pulsar timing array. For all intents and purposes, the y-axis and the x-axis, they're the same, right? This is how much the pulsars, their times of arrival are changing due to a passing gravitational wave, and this is how far they are separated from each other on the sky. The blue dashed line, it's the same line that we know, right? We just figured out what this means from our pulsar dance. It's just a little compressed down. And the black dots are the actual measurements from real pairs of pulsars observed with the nanograv pulsar timing array. And the bars above and below, these are the uncertainties in the measurements of distance and the measurements of correlation, how similarly they're moving. Now, you can see that these black dots are not really following the blue dashed line. The pulsars are not doing the dance in the way that we would expect in the spatial correlations that are described by the characteristic movement of gravitational waves. You could maybe convince yourself that they kind of go down and then they go up again, but statistically, we cannot say with confidence that we have detected gravitational waves until we see all of these pairs of pulsars doing the dance. Now, I said maybe we've detected gravitational waves. If the pulsars aren't doing the dance, why did I say that? And that's because we have detected low frequency oscillations in the arrival times of individual pulsars. What that means is we see the pulsars moving further away and closer to the Earth on timescales of years or decades that maybe are coming from a gravitational wave, but they're not doing the dance. So they may be moving slowly further and away from the Earth, but they're not all doing the dance in the specific way. And that's because our gravitational wave detector, our pulsar timing array, isn't sensitive yet. It gets more sensitive the longer you observe these pulsars. Unlike a conventional telescope that you might be familiar with, gravitational wave detectors called pulsar timing arrays, they get better with time. So this is what it would look like maybe with 20 years of data for the nanograv pulsar timing array. This is a simulation. This is not real data. This is what we think it would look like if we continued to observe these pulsars for 7 more years. You can see all of the pairs of pulsars. They're doing the dance. They're following the dotted line. They're moving in the spatial correlations that we would expect to see from a passing gravitational wave background. But we've not seen this yet, so we got to keep observing. Okay, let's recap. Across space and time, galaxies are slowly merging together. And when they do, so do the black holes at their centers, producing low-frequency gravitational waves. Now, all of the gravitational waves from all of these mergers, they add together into a low-frequency gravitational wave background. The way to detect this background is by looking for changes in the distance of pulsars. Very specific changes shown by our pulsar dance. If we see those changes encoded in the pulsar signals, we've detected the gravitational wave background. Now, that was a lot. I think we all deserve a little bit of a break. So why don't we take maybe 3 minutes or so to maybe get some water, use the bathroom if you need to, and then we'll come back and we'll talk about where this work is being done and who it's being done by. So maybe we take a quick break, and in the meantime, enjoy this live feed of the Very Large Array.
Hey, just to let everyone know, the sky is clear tonight, so we will probably be observing after the talk is done, if you want to stick around.
It's going straight through my face too. It's not gonna help me. I just want to know. Yeah. So that went wrong. Please stand. This is so much fun. This is so. I wish I could do this. So. I wish I requested to do the weight thing. I know. This would make me sitting in bed 100 for like 3 hours. I like this is the most I know you know like no letter. No, this is the most I felt for astronomy maybe since Bengali, but even we have a demo actually, so look. You use it for after, but we couldn't do it last week because of that. That's a very good demo. You want to do part? Hopefully a lot of people will have a class. Yeah, we haven't locked the date yet, but we'll send out things for volunteers and for people to be able to set up and stuff. I haven't felt this much joy since we got. I know. Since stars and radiation, I always felt like I was learning. I'm gonna be honest with you. Yeah, Bengali in person was where it was at. Bengali online. Yeah.
Maybe everyone can start to file back in and take their seats, and I'll start up again in maybe a minute or so.
Perfect. Oh yeah, that's no. Well, that's not big brain right now. How? Everyone would have paid attention. Everyone.
No, people were just paying attention to the chat where we were arguing about lightsabers.
Literally, it was just a Discord arguing and stuff.
It's a little bit hard for me to see. Are people mostly back?
Yes, we should be good to go now.
Okay, cool. All right, so we've talked about how astronomers are searching for the gravitational wave background, but we haven't talked about who is doing it and where. So there are many pulsar timing arrays from happening in different places across the globe, but the one that I am a member of is called the Nanograv Pulsar Timing Array. We are dozens of astronomers from many institutions and radio telescopes across North America, all working toward the common goal of detecting this gravitational wave background. That's my advisor, Paul Demarest, in the front, and me hiding in the back. Until last year, our collaboration used 3 telescopes: the 300-meter Arecibo radio telescope, the 100-meter Greenbank radio telescope, which is shown behind us here, and the Very Large Array, where I work now. That was used to time a handful of pulsars until recently. Now, just in anticipation of some confusion, the Pulsar Timing Array is our gravitational wave telescope. These pulsars have been beaming information about passing gravitational waves to Earth for millions of years, but there needs to be something on the other end receiving those signals. And it's taken until the last couple decades with modern radio telescopes and analysis techniques to be able to interpret these signals and basically, plug in to this galactic scale gravitational wave detector. So to see how these radio observatories work, let's tour some of them, starting 40 miles west of where I'm standing at the Very Large Array. The VLA is located on the plains of San Agustin in central New Mexico. The array is comprised of 28 radio dishes laid out in a Y configuration. This Y configuration follows over 80 miles of railroad track, allowing us to move the dishes to different locations. Now, why would we want to build a radio telescope in the middle of the desert? Now, I overheard that you guys are going to go up maybe onto the roof and observe after. Being in the middle of Long Island and having the football stadium lights pointed directly at the dome, I know you are all intimately familiar with the concept of light pollution. Well, radio astronomers have to deal with light pollution too. Our light pollution is called radio frequency interference, and it comes from all manner of electronic devices and communications equipment, from your cell phones, Bluetooth and Wi-Fi transceivers, to cell towers and Sirius XM satellites. Now, out here on the plains of San Agustin, we're sort of in the middle of nowhere, and we're surrounded by the Magdalena Mountains, which shield us from a lot of radio frequency interference. Okay, but what's with the railroad tracks? Why do we need those railroad tracks along path the VLA? Well, it's because the VLA is configurable. We can move these dishes to different locations. And the way that we do that is with these 2 custom-built diesel-powered antenna transporters that we use to reconfigure the array about every 4 months. What for? Wouldn't it be easier to keep them in one place? Well, reconfiguring the array allows us to take very different pictures of the universe by allowing us to change our sensitivity to scale. Here's an example of the same radio galaxy observed with the 4 different VLA configurations. In our widest configuration, the A configuration in the upper left, when the furthest dishes are 22 miles apart, we are sensitive to the most fine scale structures like the superheated plasma being blasted out of this galaxy's nucleus. And in our smallest configuration, the D configuration in the lower right-hand corner, we can see the diffuse structures like the woofly lobes of the jets coming out of this galaxy. This is a unique ability of the VLA, and it's what makes it such a powerful and versatile instrument. The other thing that makes it such a powerful instrument is the hardware itself. Each of the VLA's dishes are 80 feet across and weigh a whopping 230 tons. Their massive size is what allows them to collect radio light waves, like the ones coming from our pulsars. Let's take a look inside one of the dishes. At the center of each VLA dish are 8 cone-shaped structures of varying sizes. These are the feed horns, and below each of them is a receiver system, allowing the VLA to observe in 8 different frequency ranges of radio light, as low as 1 gigahertz and up to 50 gigahertz. Which of these feed horns the incoming light is reflected into is controlled by an asymmetrical secondary reflector at the apex of the dish at the top. Rotating this secondary reflector will bounce the light off of the main large dish into one of the feed horns, thus determining the observing frequency. Now, I actually have a feed horn with me. Get a little closer so you can see. This one is square, and the ones at the center of the VLA dishes are round, but that's the same principles apply. So these feed horns are specifically built to be the same size as the wavelength of light that they are trying to detect, so that the waves can fit inside of them. And they have corrugations on the inside in order to be able to help the wave fronts advance down the feed horn and into the receiver systems. Now, at the bottom, it's a little bit hard to see, but at the bottom of this feed horn, there's actually a little needle. This needle is really what we're referring to when we talk about a radio antenna. This is really the antenna. All of this stuff is just to help make sure that the light that we're receiving is only from the direction we're pointing in, so that we're not getting light coming in from other unintended directions. Now, this is a look inside the vertex room, inside where all the receivers are stored. These are the electronics that convert light into voltages and voltages into digital signals. These are the 8 receivers, 1 under each feed horn. You can actually see the feed horns, the bottom of them poking down. And the majority of the space down here is actually taken up by dewars and other cryogenic equipment, which are responsible for keeping the important electronics, which are only about the size of a postage stamp, cooled to 3 Kelvin. Next, let's head over to West Virginia to see the Green Bank telescope. Now, the Green Bank telescope is just as isolated as the VLA, but with additional restrictions. The Green Bank Observatory is situated within the 13,000 square mile National Radio Quiet Zone, where electronic use is heavily restricted. Within 20 miles of the telescope, microwave and cell phone use is outright banned to protect observations from interference. Now, the telescope itself is huge. At almost 500 feet tall, with a reflecting surface almost 350 feet across, enough to fit 2 football fields, the Green Bank telescope is the world's largest steerable single-dish radio telescope. It can see 80% of the sky with tremendous sensitivity, which is why it's so great for timing these very faint pulsars. Now, the optics of the GBT differ from the VLA in a few ways. The primary dish is shaped in such a way that incoming light rays are not blocked by the boom arm or the secondary reflector like they are at the VLA. This means that the receivers are not at the center of the dish, but up near the secondary reflector. There's the secondary reflector. And there are our feed horns again. Now, the GBT can host up to 8 receivers and a rotating turret in the receiver cabin at the Gregorian focus of the telescope. These receiver systems cover frequencies of 1 gigahertz to 100 gigahertz, so almost twice the range of light frequencies that the VLA can detect. But the GBT also has the option to host one of 5 low-frequency receivers at the prime focus of the telescope on a retractable boom that sticks out in front of the secondary reflector, shown here. Now, at higher observing frequencies, small deformities in the dish become noticeable in the observations. To compensate for these distortions, the surface of the GBT is made up of over 2,000 independent panels. Each of these panels are mounted on actuators at the corners, which can raise and lower the panels to adjust the shape of the dish's surface to a precision of ½ a millimeter. Finally, we'll visit the Arecibo Observatory in Puerto Rico. Situated in the Karst Hills 20 miles from the city of Arecibo, Arecibo Observatory used to be home to the world's largest single-dish telescope. A massive Gregorian reflector with a primary dish almost 1,000 feet across. Now, Arecibo had a very unique design. All of the optics were suspended by steel cables more than 100 feet above the primary reflector. But this also meant it was not a fully steerable telescope. The telescope's primary reflector is stationary, the big dish at the bottom. It stays at one place. And the telescope is pointed by moving the receivers and transmitters in altitude and azimuth back and forth above the dish. This means that at any given time, only a fraction of the dish is illuminated, limiting the observable sky to about a 40-degree strip. So you can see here, right, that the telescope is not receiving light from the entire dish, only receiving light sort of within that cylindrical beam of light there. So this is a simple schematic of the optics. The primary reflector, the big dish at the bottom, was composed of over 38,000 aluminum panels, which were attached to actuators that could control the shape of the dish. You could see that the light is reflected up from that spherical big dish into the Gregorian dome. Inside the Gregorian dome, we can see the secondary and tertiary reflectors and the feed cabin where the electronics are located. So if we take a look inside the dome, the secondary and tertiary reflectors were specifically shaped to correct for spherical aberration, which is the fact that, when you have a spherical big dish at the bottom, all of your light rays, they don't converge to a point. So you need to have these custom shaped reflectors on the inside in order to make sure that you are all of your light is in focus. Above the tertiary reflector and below the feed cabin, we can see the bottom of the receiver feeds sticking out. Everything here is upside down compared to the VLA in Green Bank. Since the light is coming up from the bottom of the tertiary reflector and underneath the receivers, all of the feeds are facing down. Now, if we take a walk inside the feed cabin, we can see the top of the receiver systems and their electronics. Again, most of the volume here is taken up by cryogenics, which pump around liquid helium used to cool the electronics in the receivers to 15 Kelvin. Now, the rotating turret in here hosted 9 receiver systems, including a 7-beam camera called Alpha, which was made by CSIRO in Australia. And that is why it had a little kangaroo on top of it, a little plushy kangaroo. No idea where that kangaroo is now. This is the 96-foot, 430 megahertz line feed that was used for ionospheric radar and sometimes pulsar observations. It had the advantage of illuminating the dish, but with an intrinsically narrow frequency range. The line feed snapped off and blew away during Hurricane Maria in 2017. Nobody actually knows where it landed, but I suspect some farmer in Barrio Esperanza now has a very expensive lawn ornament. My time in Arecibo was vitally important to my development as a scientist and as a person. The observatory scientists and staff were the first people to treat me like a scientist rather than a student, and the experience gave me the confidence I needed to stay in the field. This was a summer research internship I did after my junior year at Stony Brook. While at the observatory, I would hang around the control room waiting for any opportunity to go up to the platform. Receiver needs capping? Yeah, I can help with that. The feeling of being positively puny in comparison to the platform and dish below was exhilarating, and the views of the evening mist over the Karst Hills were breathtaking. It remains my favorite place in the world. When my internship there ended, all I could think about was how to get back to Arecibo. So I went to graduate school for radio astronomy in the hopes of someday being able to work at the observatory again. Here are the 80 pulsars that we, Nanograv, use these telescopes to time, the ones that make up our pulsar timing array, in relation to the rest of the galaxy. You'll notice they're all pretty close to the solar system. And that's because the closer a pulsar is, the brighter it appears, and the less stuff there is blocking your line of sight to it. Now, we observe these pulsars very often. We have to, in order to tease out that faint gravitational wave background signal. This is a map of the sky with pulsars denoted by triangles. Each blink is a week's worth of observations between 2015 and 2017. Red triangles are observed at Green Bank, and blue ones were observed at Arecibo. You can get a sense of just how vital frequent, consistent observations are to maintaining gravitational waves sensitivity. Altogether, we observed half of the pulsars with Green Bank and half with Arecibo. At least that was true until last year. I've sort of buried the lead a little bit, but maybe some of you noticed I've been speaking about Arecibo in past tense, or maybe you were already aware that this telescope doesn't exist anymore. That's because on the morning of August 10th, 2020, one of the auxiliary steel cables supporting the platform detached from its socket, tearing a 30-meter gash in the dish below. Telescope observations were suspended, pending an investigation and repair. It was the last time the telescope would be operational. But then on November 6th, things got much worse when one of the 4 3-inch thick main cables on the same tower outright snapped. The contracted engineering firms determined that there was no guarantee the remaining cables would hold the platform's weight, and the National Science Foundation decided that, for safety reasons, it would dismantle the telescope in a controlled demolition. In subsequent weeks, radio astronomers across 4 generations met online to brainstorm ways to save the Arecibo telescope. But neither we nor the NSF would ultimately determine the telescope's fate. On the morning of December 1st, the remaining cables from the tower snapped, and the platform swung into an adjacent rock cliff, tearing off the tops of the suspension towers and reducing the telescope to rubble. Now, there's videos of the collapse online if you want to watch them, but I won't show them to you because honestly, I still can't bring myself to watch them. People I know who worked at the observatory tearfully described it as sounding like the end of the world. Fortunately, nobody was injured. Now, my mourning for the Arecibo telescope and my future employment there was cut abruptly short by a very pressing matter. And that was that Nanograv and our pulsar timing array just lost telescope time for half of our pulsars. Remember, half of our telescopes were observed with Green Bank and half were observed with Arecibo. Where were we going to make up that telescope time? What telescope could possibly compete with Arecibo's sensitivity? We had to do something, and we had to do it fast. We had to make a decision about changing our observing strategy. Now, as we saw in this, with the flashes before of these different pulsars, regular timing observations are incredibly important. So losing a period of time of observing those pulsars is going to create a dip in our sensitivity to the gravitational wave background. That's where I come in. My role in Nanograv is sort of like a strategist. My job is to figure out how to best balance, my job and my thesis are about how to balance telescope resources, right? Pulsar timing arrays and trying to detect the gravitational wave background, they're about timing pulsars, but they're also about balancing telescope resources, right? Arecibo was a really sensitive telescope. It was a really big sensitive telescope, but it could only observe a small part of the sky. Meanwhile, Green Bank was less sensitive, but it could observe a larger area of the sky and therefore more pulsars. So how do we balance those telescope resources, and how do we make a decision about that quickly? We couldn't go and test each of these pulsars at all of the different radio telescopes because that would be too time consuming and it would be expensive. And we didn't have a lot of time to try to make these decisions before changing our observing strategy. Otherwise, we would lose significant sensitivity to our gravitational waves. So what I did was I programmed a galaxy full of our pulsars, as well as all of the telescopes that we used to observe them, inside of a computer. And then I simulated hundreds of different timing observations with different telescopes. This was the optimal strategy we came up with. So before the collapse of Arecibo, we split our pulsars almost exactly evenly between Arecibo and Green Bank, shown there on the left. After the collapse of Arecibo, what our simulation showed was it would be best to remove 7 Arecibo pulsars from the array because their contribution wasn't worth their telescope time. 41 pulsars would split observations between the Green Bank telescope and CHIME, a new telescope in British Columbia, which could time up to 10 pulsars at once. 15 would split time between the VLA and Green Bank, and 18 would be timed only with the Green Bank telescope, and then our best pulsar would be timed everywhere at the middle of that Venn diagram. We began this new observing strategy in the spring of 2021. Now, we will take a hit for the 6 months without any observations of those 40 pulsars and the ultimate loss of Arecibo, but we did manage to mitigate disaster for our experiment. Preliminary analysis of our next data release, containing 3 more years of pulsar timing measurements, is currently ongoing, and we've still not ruled out that the gravitational wave background is in our data, but we can't be certain that it's there either. Ultimately, we're confident that with the next generation of radio telescopes, like the next generation VLA, which has been funded by the National Science Foundation and construction will begin in a few years, we believe that pulsar timing will churn out gravitational wave detections on the regular, but we'll just have to wait and see. Thank you for being such an attentive audience. I really had fun preparing this talk and talking to you. Now I'll take any questions you have.
All right, so if anyone has any questions, I think what we'll do is we'll have you actually come up here to the podium at the front so that you can talk and be heard on the Zoom call and both in the microphones, everyone can hear you.
You could probably wave hi in the little camera over here too when you're walking up.
Yeah, and what I'm thinking, if it's okay with you, Tyler, is I'll actually put up the QR code now for that survey you wanted everyone to fill out so that people can kind of work on that while we're going through questions. Does that work?
Yeah, fantastic. Yes.
Okay.
Thank you in advance, everyone, for filling out the survey. It's really going to be important in me trying to understand, this is not to test, your intelligence or anything like that. This is to evaluate myself on how well I was able to convey, these concepts. So thanks in advance.
Yeah, all right. So I will go ahead and the survey QR code is already up for everyone in the room here. I'm just going to try to screen share it on Zoom also so that people on there can fill it out as well. Okay. There we go. It looks like maybe our first question is from someone on the Zoom actually. Let me just make sure I have it set up so that people can unmute themselves on Zoom now. All right, so Kay, I think you have your hand raised. If you want to get started asking your question, go right ahead.
Kay, if I'm not sure if I can hear the person that asked the question, but I can actually see their question in the chat. So I can answer it, but I can't hear them. So maybe I'll just go ahead and answer it. The question was, in the scene where the Earth was covering up my middle and I was surrounded by the ring of pulsars, why was the Earth static and not being pushed, pulled, squished, or elongated like I was in the position of the pulsars? Very, very, very good, observation. You were watching very closely. It should have been. Let's go back to that. Oh, they said they're on mute. The host disallows unmuting. So maybe they're not able to unmute yet. But let's go back to that. Where was that? Here we go. Right. So, nope. So Kay was asking, why is the Earth not going like, it should be. It should be. That's really what's happening. I wanted everyone to focus really on what the pulsars were doing, but you're absolutely right. Just like I'm expanding and shrinking and the pulsars are moving closer to and further away from the Earth as the gravitational wave passes in this direction, so too is the Earth, kind of wobbling very, very, very slightly. Great observation. Hopefully that answers your question.
Come on up.
Yes, Giancarlo, come on up. Wave hi in the camera too, just so Tyler can see you as well. All right.
Oh, so yeah.
Giancarlo, the camera's right there. Right over there.
On this side. Hi, Tyler.
All right, just wave hi
Hey.
for Tyler, just so you can see a little more back, Giancarlo. All right. Here you go in the mic, just so you can hear you properly.
I had one question about pulsar observation. If pulsars are known for being extremely predictable and many have very short periods, would it not be rather straightforward to mitigate the loss of such data if we probably have thousands of data points for pulsars?
That is an excellent question. I alluded to this a little bit, but I didn't really go into it, and I can do it a little bit now. So yes, these pulsars are spinning extremely quickly. We know their pulse arrival times to the precision of about a microsecond for some of them. For others, it's tens or dozens of microseconds. It would be an easy proposition to see that characteristic motion of gravitational waves in these pulses if that was the only thing that was changing the distance between the Earth and the pulsar. But remember that the Earth is going around the sun. And so on the period of a year, the Earth is also getting closer to and further away from the pulsars. Also, there's stuff, electrons, gas, dust, in between the Earth and the pulsar that are impeding the travel of light from the Earth to the pulsar. Some of these pulsars, they're also in binary systems, meaning the Earth is going around the sun, and then the pulsars are around here going around in binary systems, and there's all kinds of crazy stuff happening. So in order to be able to see the very, very, very faint signals of gravitational waves, you need to be able to model all of those other effects, and you need to be able to remove them, leaving behind only the gravitational wave signal. Excuse me, that is much harder to do because it means you have to, I'll give you a quick example. We thought we had detected gravitational waves a couple of years ago. It turned out we were using the solar system ephemeris from NASA's Jet Propulsion Laboratory. That's what NASA uses to send their probes to different planets and moons and stuff. You would think that that would be extremely accurate, and it is. It's accurate enough to send a probe to a planet or a moon, but it is not accurate enough for pulsar timing detection because it doesn't tell us exactly where all of the positions of the objects in the solar system are to the precision necessary to be able to measure the change in distance between the Earth and the pulsar of about a foot. So that's why we need more data, we need more pulsars, and we need to measure them with better precision with better telescopes. Hopefully that answers your question.
Giancarlo,
Yeah,
can you
makes
just
sense.
repeat
Thank
your
you.
question very quickly? Just so people in the chat also can catch it again.
And just to repeat, what I asked was because pulsars are extremely predictable, often with fairly short periods, I would think it would be straightforward to just mitigate that loss because we already have thousands of data points. So I asked, why wouldn't that necessarily be so?
Thank you so much, Giancarlo. We really appreciate it.
Thank you.
We
Great question.
also see in the chat there is a question by Henry. Actually, Henry, you have your hand raised. If you want to unmute yourself, you can absolutely do that. If you want to type it in the chat, you can do that as well.
Okay, thanks for your presentation. I really enjoyed it and I found it fascinating. So my
You're welcome.
question is, what is a typical day for you on the job and what are observing sessions like?
Oh, that's a good question. Typical day on the job. It's really changed over the course of the past few years as I've gone through my PhD. I'm taking my last class now, so most of my time is not spent on coursework, whereas a significant amount of my time, I would say, I don't know, maybe 75% of my time during the first 4 years of my PhD was spent, just like doing homeworks and going to class and stuff and studying. Now it's really kind of varied. Before COVID, I would go out occasionally to work at the VLA. Most of the time I've been working remotely in the past couple of years. My job mostly revolves around making computer simulations, so I'm sitting in front of the computer a lot. But I also do stuff like this, outreach stuff part-time. So every now and then I'll, work on a fun presentation like this, or yeah. So it really does vary, but mostly in front of the computer.
All right, thank you so much for that question. Does anyone have any other questions they want to ask Tyler?
We have.
Yeah, go right ahead.
You are good, Toby.
So first of all, thank you so much, Carol, thank you so much for your talk. Ashita and I were wondering how you made this talk sort of in an audiovisual perspective. When we're giving presentations, it's not nearly the level of PBS space-time vibes that you had. So we're wondering, like, what technology did you use, and is there anything that we can steal to amp our presentations up?
Maybe it seems like I'm in a studio or something like that, but let me pull down the curtain here so you can really see what we're working with.
You're secretly in space.
I'm secretly, yes. How are we going to do this? I am actually in my office. I guess we can just do this.
Oh, wow.
I prepared this talk because I was asked a few months ago to do a talk for another astronomical society in New York. And I'd never given I had given lots of, PowerPoint talks. But over the past few years of COVID, I was so sick of listening to PowerPoints. I was so sick of making PowerPoints. I was so sick of the standard, like Zoom framing of like, I didn't want to do that. And if I was going to make an hour-long talk, it had to be visually appealing and entertaining. And also, I started working on this project, the Gravitational Wave Project, 4 years ago at this point. And so in the process of explaining these really, really difficult to understand concepts to people, I knew I needed to use the demonstrations and the visualizations that had helped me understand when I was learning about these things. And that was the dance, and that was the power drill thing. And the only way that I could do that was using some kind of visual medium. And the only way I could figure out how to do that was with a green screen. So this is actually a $40 green sheet that I bought on Amazon. I'm using my iPhone. Maybe I can share my screen. I don't know if that's going to work. I'm using my iPhone. I actually have two phones, the iPhone and then another old phone that was pointed at the sort of gridded sheet demo. But let's see if I can share the software. The software is OBS. If some of you, I don't know, stream on Twitch or whatever, maybe you're familiar with it. It's a completely free software. Can I do screen sharing?
I think Ashita should be giving, oh, there you go.
Yeah, there we go. I'm using OBS. All of my visuals are controlled, through OBS. And then I am using this in order to capture the video from my phone. I'm using this software, also free software called Camo. It's an app that you download on your phone. My goal in preparing this presentation was basically to the talk that I was giving was they were going to give me a $300 stipend, and my goal was to not spend more than $300 putting all this together. So all this stuff was like, off of Amazon, green sheet, free software. It's kind of crazy what you can do with like, just a green sheet, a smartphone, and some free software. So hopefully that sheds a little light. I mean, it took me a while to put this all together, but it was actually not as hard as I thought it would be. I thought it, I didn't know if it would work or not. So.
Awesome, thank you so much.
Sure.
So any final questions for Tyler? Awesome. Well, if not, please everyone give him a round of applause. Like, absolutely phenomenal. Every single one of us enjoyed it so much. We haven't seen such an engaging presentation in probably forever. So we really appreciate you taking the time, entertaining us and educating us. And we really hope you come back, stay in touch with the club. And thank you again so much for this. We loved having you here. Really appreciated it.
Definitely, you're welcome. Thanks so much for having me. And I'm really, really happy to see how much the club has grown and all the stuff you guys are doing. So keep at it.
All right, thank you so much. Have a great night. And once again, thank you from the Astronomy Club. Really appreciate it.
All right, clear skies, everybody. See you later.
Clear skies. All right, thank you.